Okay, so we'll start with module 2, which is going to be on what are called as van der Waals interactions. So this is going to be the content that I would most likely follow throughout this module. We will start with talking about molecular origin of van der Waals interactions. So that would need a little bit of intro to dipoles, induced dipoles. Then we will talk a little bit about molecular interaction between ions and molecules. That is important for us to have a background, because we are going to extend that concept to van der Waals interaction between particles later. Okay. So, therefore, we will start with talking about van der Waals forces in molecules and atoms, and then we will try and see how can we extend those concepts to talk about van der Waals interaction between particles. Then we have bunch of things which concern van der Waals interaction between particles. We will discuss a little bit about scaling of van der Waals interactions and derive an expression for van der Waals interaction between different objects. We will introduce the concept of Hammacher constant, because when we talk about van der Waals interaction between atoms and molecules, we need information about dipole moment, we need information about something called as a polarizability, we need to know something about the frequency of vibration of atoms and molecules. Okay, all of that are required for you to estimate what is the van der Waals interaction between atoms and molecules. Now, in order to calculate van der Waals interaction between molecules, all the physical parameters are kind of clubbed together into a constant, what is called as a Hammacher constant. We will try to tell you a little bit about how does this come about. Followed by so there are some theories that people have developed, which are useful in obtaining the van der Waals forces. For example, we are going to touch upon a theory where we are going to show that this Hammacher constant, on which the van der Waals forces depend on, you can obtain that from bulk properties of the materials, like by measuring surface tensions or by measuring the dielectric constants. So, we will try and relate the Hammacher constant to some measurable properties of the materials, and then we will see how that can be used for obtaining van der Waals interactions. Finally, we will talk about it turns out that the when we say that van der Waals interaction between two particles, it is also important in which medium you are putting the particles. Is the medium in which the particles are present, is it water, is it air, or is it vacuum, right? So, the medium in which the particles disperse is also important. So, in that context, we will talk a little bit about what is the effective medium on van der Waals interactions. So, how does the presence of a medium affect the van der Waals interactions? And then finally, we will end with talking something about combining relations. These combining relations are useful when you have information about the van der Waals interaction between two atoms or molecules or particles in vacuum. I can use that information to obtain van der Waals interaction between the particles in any medium. Okay. So, therefore, these combining relations become important. So, this is what is going to be the flow of this particular module. Just a bit of introduction. One thing that you should be aware is that the van der Waals interactions are always present. Okay, you take any colloidal system, be it particles in a fluid, association colloids in a fluid, or any colloidal dispersions you talk about, the van der Waals interactions are always going to be there. Okay, that's okay. They are the most important forces in colloids and surface chemistry or physical chemistry or colloids and interfacial science. So, these van der Waals forces have their origin, they originate because every atom or a molecule will have some dipoles and induced dipoles which are inherent to these molecules or atoms. will again discuss some of these terms as we go along, and therefore, such interactions they are really important when you want to really look at any aspects of material study. Okay, whether you are trying to look at formulating new materials, whether you are trying to tailor some properties of the material. So, these become very important. In a nutshell, there are actually 3 subclass of interactions which contribute to van der Waals. Okay, that means if you have the total van der Waals interaction, it has contributions from something called as D-Bay interactions. These D-Bay interactions are interactions between two permanent a permanent dipole and a induced dipole. Okay, that is the D-Bay interaction, and something called as a key sum interaction, which is interaction between two permanent dipoles. Okay, if you have two permanent dipoles and the interaction between them would be phi key sum, and what is called as the London dispersion forces or London interactions, which is interaction between induced dipole and induced dipole. Okay, you take any material, it could be like say if you have a container with water, okay, or any liquid or any condensed phases, okay, you will see that there will always be van der Waals interaction, and this interaction would be combination of the interactions that come because of what are called as D-Bay interactions, key sum interactions, and London dispersion forces or London interactions. Okay. So, before we talk a little bit about each of these things, we will try and do a very quick intro to dipoles and induced dipoles. Okay. So, all of you already know a dipole, it is essentially a pair of electric charges, okay, which are of equal magnitude, okay, but they have opposite sign and they are separated by some distance d, and for that you define something called as a dipole moment, which essentially is the product of the magnitude of the charge multiplied by the distance, right. That is what is a dipole. And typically whenever you represent dipole, you start with a line starting from the negative charge and you kind of draw an arrow, and the arrow typically points from the negative to positive. Okay, that is a typical convention that people use. That is what is called as a dipole. Okay. Let us talk a little bit about what is called as a permanent dipole. Okay. Any thoughts? What is a permanent dipole? Some thoughts?
So, like water molecule has a permanent dipole.
Yeah. So, water molecule has a permanent dipole, right. Whenever you would seen water molecules, people represent something like this. Okay, that is your oxygen and that is your hydrogen. Okay. People typically say oxygen end will have some negative charge and okay, the hydrogen end will have some positive charge, right. Okay, that is an example of a molecule which has a permanent dipole. Okay. So, of course, you can think about other examples, right. HCl is another example, hydrochloric acid. Okay. So, typically permanent dipoles are found in molecules in which one of the atom is strongly electronegative. Okay, when one of the atom is strongly electronegative. Okay, if you take the case of HCl, it turns out that chlorine has 7 electrons in the outermost shell. Chlorine has 7 electrons in the outermost shell, and it wants to share an electron with hydrogen. Okay, so that it can complete its outermost shell, right. So, therefore, typically what will happen is when you talk about sharing of electrons, we talk about covalent bonds, right. In covalent bonds, it is and the electrons that are shared, they kind of belong to both the atoms, right. And because chlorine is a strongly electronegative atom, what it does is it will pull the electrons a little bit towards itself. Okay. So, because of which the end of the molecule which has a strongly electronegative atom acquires a partial negative charge, and the end which has a less electronegative atom will basically achieve a it will have a slight positive charge. Okay. So, therefore, whenever you have many such molecules, what will happen is there is going to be. So, if I take for example, another HCl molecule, again I can write a similar configuration. This end is going to be slightly positively charged, this is going to be slightly negative charge, and there is going to be a attraction between the two molecules which have permanent dipole. Okay. So, therefore, and so typically molecules which have mirror symmetry, for example, oxygen, methane, CO2, all these molecules do not have permanent dipoles. Okay. One of the requirement for a molecule to have a permanent dipole is one of the atom or molecule has to be more electronegative than the other molecules. Okay. That is what is called as a permanent dipole. Okay. So, then what is called as induced dipole. So, induced dipoles, what I can do is there could be an atom or a molecules which is a neutral atom or a molecule. Now, so if an ion approaches such a neutral atom or a molecule, or if I have a molecule which has a dipole, if that approaches a neutral atom, what will happen is, so it will disturb the electron cloud around the neutral atom. So, because of which the neutral atom can also be polarized, it can also acquire either positive or negative charge depending upon whether it is approached by a cation or an anion, or which end of the permanent dipole is near to the neutral atom. Okay. That is what then what I would say that there is a dipole that is induced in the neutral atom. Okay. The other ways by which you can have an induced dipole is that even if you take a neutral atom, okay, we know that if you look at electronic structure, you have a nucleus, okay, then you have different orbitals, right, and the electrons are kind of revolving around these orbitals, right. Now, what will happen is, but of course, because they are continuously, they are not fixed in space, right, they are continuously changing their position. What will happen is there could be momentarily there could be a case, there could be some imbalance in the distribution of electrons in these orbitals, because of which one end of the atom can have a more number of electrons on one side compared to the other side. Okay. And that depends on it's a probabilistic process, right. So, therefore, what could happen is, even in a neutral atom, at momentarily there could be a case where one region of the atom is slightly negatively charged, and correspondingly the other end will have a positive charge. Okay. So, therefore, induced dipole can be either can occur if you have a neutral atom, and if an ion or a permanent dipole approaches a neutral atom, or the fluctuations in the electron position can also lead to induced dipole. Okay. So, therefore, we go back to again now these interactions. Now, we know each of these terms. So, therefore, this d-Bay interactions are the interaction between a permanent dipole and a induced dipole. Okay. You could think about a case like this, right. There was a permanent dipole, okay, and then in the case of a neutral atom, okay, you could have one way to think about this would be that, let us think about a case. see water has a permanent dipole, right. Now, if you look at some organic species, okay, which is say sparingly soluble in water, okay. So, we know that typically organic molecules will not have a permanent dipole, right. They are what are called as non-polar, right, and water is an example of a polar molecule. If you have cases like that, then you have some molecules which have a a permanent dipole, right, okay, and some non-polar species which does not have any charge. Okay. Therefore, you can think about an interaction between a permanent dipole and a induced dipole, right. Or if I take an example where I have only non-polar molecules, okay, then what will happen is they will have what are called as induced dipole interactions. Okay. That will be the more dominant interactions. Correspondingly, if you take something like water molecule which has known to have a permanent dipole, then the permanent dipole interactions are going to be more dominant. Okay. So, these are this is a table which lists all the molecular interactions, okay, between atoms, or ions, okay, or the molecules that constitute matter, right. So, I will just quickly go through this table. That is a description. It will tell you what is the interaction between. In this case, this is an interaction between ion 1 and ion 2, and that is an expression for the interaction potential. Okay. So, ion 1 has charge Ze, okay, the valency multiplied by the charge on the electron of one ion. Similarly, Ze2, that is the valency again multiplied by E for the second one, and 4 pi epsilon naught x. Okay, that is the interaction potential for two ions, right. And so, therefore, this goes as 1 over x. Okay. So, the general form is phi going as x power minus n for this case is 1 because you have 1 over x here, right. Similarly, you can think about interaction between an ion and a dipole. Okay. In this case, the ion will have a charge Z E1 again. Mu 2 is the is a permanent dipole, is a dipole moment of the dipole 2. Okay. Therefore, it is mu 2 here, and cos theta is the angle, right. For example, I could have a dipole here, okay, and my ion could be here, right. That the theta refers to the angle, right. And so, it has a 4 pi epsilon naught x square dependence. Therefore, your exponent is going to be 2. Okay. So, I can go on so on and so forth. Okay. I can derive an expression again for the interaction between two permanent dipoles. In that case, it will go as mu 1 mu 2 divided by x cube, your exponent is 3, right. So, we have done these exercise already, right. One exercise we have done in the class, right. So, if you look at the potential energy of interaction between two ions, okay. So, I said that the interaction potential, if you want to calculate, is the negative integral of the force times the distance, right. The force, if you take two ions, it goes as q1 q2 divided by 4 pi epsilon naught into 1 over x square. So, if I integrate that out, right, you get u to be q1 q2 divided by 4 pi, so 1 over x, right. This is exactly the first entry. Okay. So, if I rub this up, right, that is actually your first entry. Only thing is q1, q1 is Ze 1 and q2 is Ze 2, and you have 4 pi epsilon naught, that is this one, and 1 over x, right. I can do the similar thing for potential energy of interaction between an ion and a dipole, right. So, I have a ion whose charge is Ze, okay, and there is a dipole, okay, something which in which you have two charges of equal magnitude, opposite sign, separated by some distance, in this case L, okay, and this distance is okay, r12, right. So, I can write a similarly, I mean this first term, so this is Z e times q, okay, Z e times q divided by 4 pi epsilon naught into 1 over distance between the two, right. This is r12, okay, plus L by 2, because if you say that L is a the distance between the, so this distance is going to be L by 2, right. Okay, so therefore, this is going to be L, right. This is a small mistake, right. This is going to be, right, because if you look at
R12 is from the center of the dipole.
what's that R?
R12 should be from the center of the dipole.
R12 would be, yeah. So, yeah, if you, yeah, that's true. Let's do like that. Okay. So, now if I look at this, okay, let's do that, right. Yeah. So, if I say that R12 is the distance of the center of the dipole, okay, from okay, is the distance from the center of the dipole to the ion. Therefore, the distance the distance that the q plus q is from the ion is r12 plus L by 2, right. Similarly, this is going to be at a distance r12 minus L by 2, right, and I can simplify this a little bit. So, I can just do the, right. So, therefore, your denominator becomes r12 square minus L square by 4, okay, and this gets cancelled, okay. So, minus L by 2 minus L by 2, that is L, okay, and the Z e times q, the q times L is clubbed because that is a dipole moment, okay, cos theta. Now, in this case, what will happen is, because you have, okay, this is for a case where I have a, okay, let us not for a moment consider this is not there, okay. So, I have Z e here, right, that is this term, q times L and the negative sign that comes because of the, there was a minus L here, right, and 4 pi epsilon naught. Now, if you consider a case where this R12 is much larger than L, I can kick this out, therefore, it becomes 1 over distance square, okay. Now, I can do a similar exercise, but for a case where it is an oriented dipole, right, this dipole is oriented at a particular angle to the ion that I have, okay, then this theta becomes important. I could similarly, if r minus and r plus are the distance of these two charges which make up the dipole, I can actually write the total interaction energy is Z e q divided by 4 pi epsilon naught into 1 over r plus minus 1 over r minus. These are just these two separation distances, right, okay. And of course, I can derive an expression that connects these distances to r12, right. I can do that. Again, if you use the approximation, if you do some simplification, it turns out that the interaction between the ion and the dipole for any arbitrary orientation, okay, goes as Z e q L cos theta divided by 4 pi epsilon naught into 1 over distance square, okay. So, that is this term, right. So, similarly, I could do a construction and I can actually also get what is the interaction between the two, right. If you want to think about, I could take 2 dipoles plus q minus q, okay, again another plus q minus q, right, and I can get the separation distance to be x, okay. If this is the L and L are the the distance between the ions that form the dipole, I can either take a fixed dipole, that dipoles are fixed in space, and I can calculate what is the total energy of interaction exactly similarly, right. So, you can do that, right, you know how to do that, right. So, if you go back here, so when we did the two dipoles, it is the interaction between this plus the interaction between this, right. Similarly, if you have a dipole interaction, is the interaction of these two plus these two, okay, these two plus these two, there are going to be 4 terms, right. You can simplify that. If you do that, then you will end up with a expression wherein you will have 1 over x power 3 dependence. Okay. Now, okay, so this is again the same table, right. So, if you look at you know the expressions for phi, right, this phi can be either positive or negative. That means, the interaction can be either repulsive or attractive, depending upon whether you are dealing with ions of same charge or So, therefore, in the table that I showed, there are some entries which sign may be positive or negative. It depends on the kind of ionic species that you are dealing with. Okay. However, there are a few entries, okay, which are marked here, okay, that is a permanent dipole induced dipole interaction and a permanent dipole interactions and induced dipole interactions. They are always attractive, okay, and all of them have 1 over x power 6 dependence. Okay. All of them have 1 over x power 6 dependence. Okay. So, these 3 entries which are always attractive and which have 1 over 6 dependence are what are called as van der Waals forces. Okay. So, that is your phi d Bay, okay, phi Keesum and phi London. Okay. So, because let us look at this, right. This is an interaction between 2 permanent dipoles. Of course, it should depend on the magnitude of the dipole moments, okay, and this is 1 over 4 pi epsilon naught that comes from the electrostatics, right, and you have kBT, the thermal energy, and 1 over x power dependence. So, therefore, the terms which have only dipole moments, they are the Keesum interactions, because they are the interaction between the permanent dipoles. Okay. And if you look at the d Bay interactions, which are interaction between the permanent dipole and the induced dipole. So, you have these are the dipole moments, okay. Then this alpha 01 and alpha 02, these are what are called as polarizability, okay, which tells you something about I talked about this induced dipole, right. So, I said that okay, I said that I have a neutral atom, okay, and I said that if I have if a charged species approaches a neutral atom, or if a permanent dipole approaches this neutral atom, I say that this can acquire, okay, this can be polarized, right. Okay. The extent to which, okay, the approaching atom or a molecule or a charged species can influence the electron distribution, okay, or distribution of electrons in the cloud, okay, is basically measured by alpha. Okay. So, higher so for some molecules it may be easier to influence the distribution, okay. So, we say that they are highly polarizable, but for some it may be very difficult to influence the electron distribution, okay. They are less polarizable, okay. So, alpha tells you something about the polarizability, okay. So, therefore, the term that have the polarizability and the dipole moments would be the d Bay interactions, because that is the interaction between a permanent dipole and a induced dipole, okay. And the third contribution, London dispersion forces. So we know what is alpha now. Okay, again 1 over x power 6 dependence. H is, what is H? Planck's constant, right? Yeah, Planck's constant, and this nu 1 and nu 2, okay, they are what are called as the frequency of vibration, okay, of the atoms and the molecules. Okay. Now, for a given atom or a molecule, if you know all these parameters, I can plug in all of them and I can actually estimate what is the van der Waals force of interaction. Okay. So, we have done that. So, this phi attractive or phi van der Waals is essentially the summation of the 3, okay, because everything has 1 over x power minus 6 dependence. I have taken x power minus 6 out here, okay, and this 1 and 2, right, 1 and 2 correspond to 2 atoms or 2 molecules, right. Now, if I have identical atoms, if I talk about just water molecules for example, then your 1 is equal to be 2, right, because we are talking about interaction between same atoms or same molecules. Okay, this expression is for 2 atoms or molecules which are not identical, but if I have identical atoms or molecules, for example, if I am worried about the van der Waals interaction between water molecules, okay, in a container which has only water, then your 1 is equal to 2, right, because you are talking about interaction between like atoms or like molecules. Therefore, your alpha 0 1 will be equal to alpha 0 2, right. Therefore, I have written this as 2 times alpha 0 1, again mu 1 is equal to mu 2 because the dipole moment of water will be the same, right. Therefore, this becomes 2 times alpha 0 1 mu 1 square. Similarly, this term will simplify to 2 by 3 mu 1 power 4, right, divided by k b t plus 3 h by 2, this becomes 2 nu and 2 gets cancelled, right, and then I have nu square here, again 1 nu gets cancelled. Therefore, you have 1 over nu and you have alpha 0 1 alpha 0 2 which will be alpha 0 1 square, right. Okay. Now, this prefactor is actually called, is given like beta 1 1, right, 1 1 because again it is an interaction between same identical molecules and that has x power minus 6. Now, you should think about similarity of this attractive part to phi Leonard-Jones. Remember, we wrote this as x power minus 12 minus beta x power minus 6, right. This part essentially is the van der Waals interactions, right. Okay, so, now we know where does this come from, right. This essentially comes from the van der Waals attractions, okay, which has 3 parts, okay, London dispersion forces, Keesum interactions and Debye interactions. We did not derive expression for this, we kind of know how they come about, and you should be able to identify each of these terms to have an idea as to which one is phi L, which one is phi D and which one is phi K. So, I just want to so this is a table. It is a really good table. I think you can learn a lot about van der Waals forces from this particular table. So, this is a compound, okay, the molecules of interest to you, and that is mu, dipole moment, its units is dBA, right. And if you look at like say so, if you look at this term, right, if you look at this expression, you have 1 over 4 pi epsilon naught whole square and there is alpha 0 1, right, alpha 0 1. So, it is actually this term, okay. So, right. So, alpha. So, basically this will give you what is alpha, okay, the polarizability, right, and that is beta, okay, that is this term, right, beta 1 1. And this tells you about the percentage contribution, okay, and we said that there are 3 contributions, okay. What is the individual contributions to the total van der Waals force of interaction, okay. That is the key-sum interaction, that is between permanent dipoles, okay, that is London induced dipoles, and dBA between the permanent and induced, okay. What can you say about this table? Look at these numbers. I want you to make a comment about what can you say about this table. This is a unique feature over the number that you have here, okay. That feature is that you look at this entry, is always non-zero, okay, always non-zero. That means you take any atom or any molecule, London dispersion forces are always present, okay, right. That is one thing. And if you look at the other two terms, right, there are cases where this is 0 here, 0 here, 0 here, right. So, therefore, depending upon the molecules that you work with, okay, this key-sum and dB interactions may be there, may not be there, but the London dispersion forces are always present, okay. And let us look at cases where, if you look at London dispersion forces here, right, here for these two molecules, which are benzene and CCl4. Again, CCl4 is again another example of a symmetric molecule, right, symmetric molecule where only induced dipoles would be present, okay. So, the cases where for the non-polar molecules, okay, for non-polar molecules, you will see that the contribution of London dispersion forces would be highest. Examples are benzene and CCl4, okay. However, on the other hand, if you take molecules which have permanent dipoles, for example, water, right, or if you take even ethanol, right, okay, they are example of polar molecules, right. And if you look again the numbers, it turns out that the contribution of the permanent dipole interactions is highest for such molecules, right. So, if I look at water, so 84.8 percentage is the phi k, okay. And if you took ethanol, you will see that again, of course, the London dispersion force is also important, but there is a significant contributions from the phi k itself, right. So, therefore, so I can say that this phi k plus phi L plus phi d divided by the total phi, right, phi total, phi or phi van der Waals, should be equal to 1, right. That is what it will turn out, right. So, if you look at this number, that is 5.5 plus 6, right, that is going to be 11.5 plus 88.5, that is going to be 100 percentage, right. Okay, so that is yeah, go ahead.
So this induced means the two entities should come and they will be induced because of the presence of the other.
So these induced dipole, I talked about two ways in which this induction can occur, right. One is if I have a container, which has a mixture of both neutral molecules and charged molecules, okay, right. That is one example. But even in cases where I have only neutral molecules, okay, the disturbance to the distribution of ions, the electrons in the shells, that can also lead to induced dipoles. So, if you look at, for example, see like for example, if you look at like say benzene, right, benzene. So, you see, I mean, everything comes from the induced dipole interactions. Okay. That means, if I have like say a container which has benzene, right. Now, you will have only every benzene molecule will only see other benzene molecules, right, but the fact that they are also neutral, okay, yeah, it is not because of the it is not that one benzene molecule will come near another benzene molecule and it will induce a dipole, it will induce the formation of the dipole. Okay.
Sir, I think what he asked is,
Yeah.
suppose there is a neutral atom.
Yeah.
Can an induced dipole induce charge on that neutral atom?
Yes.
Okay.
Yeah. Right. That's what. If I have a neutral atom, if a charged species comes near it, of course it can disturb the distribution of ions in the around the.
So my question was
Yeah.
like, so benzene as a whole doesn't have dipole moment, I think so.
Yeah, it doesn't have a permanent dipole.
Yeah, permanent dipole.
Okay.
So I'm thinking if two benzene molecules come together,
Yeah.
then both are getting induced. That's why it's called induced interaction.
No, what will happen is this, right? Okay, let me just make that point that's clear. So that's a good point. So what he's trying to say is this. See, one thing that is important is that see, for the induced dipole interactions to to occur, the orientation of the molecule is also important, right? Okay, the orientation of the for example, if I have like say HCl molecule, okay, which is say this is slightly negative, this is slightly positive, right? Now, if only if a Cl minus end comes near H plus, there is going to be attraction, right? Okay, so anyway, so in the case of induced dipole, what will happen is this, right? Now, I said that because of the fact that the electrons are not mobile, they are moving around, there is going to be a fluctuation in the electron density, right? That means, if I take even a neutral atom or a molecule, okay, if you look at some regions of the atom at some particular instant in time, they may have a higher density of electrons compared to other regions. Okay. So, therefore, the region where there are more electrons will acquire a negative charge, and the region where there is less electrons will acquire a positive charge. Now, this will happen for, as I said, right, this only occurs momentarily, and this can happen for, may happen, may not happen, it is a statistical process, right. It can happen for a large number of molecules which may be in a container. Now, if the orientation of the molecules are such that, okay, if there is another again a neutral atom which has been polarized because of the change in the fluctuation, right. Therefore, so if there is a negative end, and there is going to be, so if you sum up all the interactions, such interactions, it will turn out that, okay, the overall interaction is going to be attractive. Okay, it will go as 1 over x power 6 dependence. Okay, yeah. Maybe we can read up a little bit about it. Okay, so what I will do is, I mean, so yeah, so maybe I will just stop here. Okay, so we have kind of talked about the van der Waals interaction between atoms and molecules. I have introduced you different terms. We know where the van der Waals interactions come about now. Okay, so we will try and extend these concepts to van der Waals interaction between colloidal particles. Okay, if I have colloidal particle 1, colloidal particle 2, okay, so we will see how do we think about van der Waals interaction between particles in the next class.